Good afternoon, everyone, and welcome to today's seminar titled AI Meets Complex Flows, Lagrangian and Eulerian Data-Driven Tools for Optimal Navigation, Optimal Odor Searching, and Data Assimilation. Our speaker today is Professor Luca Bifarale, who is a theoretical physicist, full professor at the Department of Physics of the University of Rome Tor Vergata, working on out-of-equilibrium statistical physics, high-performance computing, and data-driven tools applied to complex flows and complex fluid problems. He is the author of more than 280 scientific papers, which collected more than 10,000 citations. He has been divisional associate editor of Physical Review Letters, elected as fellow of the APS and Euromec. He has been awarded 2 advanced grants from the ERC. Professor Bifarale, I would like to thank you very much for accepting to be our speaker today. We are looking forward to your talk.
Thank you very much. Please let me know if you hear me, if everything is okay. Yes?
We can, yes.
Okay, great. Thank you very much. So thank you for the invitation. It's a great pleasure to be with you, even though somehow at a distance today. So I prepared today a sort of overview of what people in my community, in computational fluid dynamics community, are doing concerning data-driven applications to attack in a quantitative way, and I would like to stress the word quantitative, in a quantitative way, problems using data-driven or machine learning tools. And the typical problem is somehow I tried to present you in this way. It could be a sort of data augmentation that you have image. These are tools that are very well known in the computer vision community, where you have pictures that are damaged and you want to guess what is behind your damaged. Or this is what I would call a sort of Eulerian problem. That is when you have the whole field and in space, and you want to fill gaps in space. Or you may have problems that are in our sense, in our community, called Lagrangian. That is a problem where you need to refill missing information on a one-dimensional string. Here could be, for instance, the title of our seminar. So the goal is to translate this kind. Oops. Okay, now again, the slide does not. Okay, so the goal would be to try to translate this kind of to move from the gappy data, Eulerian or Lagrangian, to reconstruct the information and to have and to disveil finally either the whole figure, the whole picture, or the whole content in the sentence, in the title, or that you want to discuss. So I will move from these problems that are well known in semantic languages, reconstructions, or data augmentations in computer vision community, and to understand how you can rephrase these kind of problems in our field, in the field where you have fluids, complex flows, and in particular computational fluid dynamics problem. So the talk is split in 3 main parts. I will, because I guess that nobody is, not everybody is expert in fluid dynamics. I will have a very short introduction of what are the main problems that might be of interest for a theoretical physicist and for a computational physicist in fluid dynamics, and in particular in turbulent flows, whenever you want to deal with turbulent flows. And then I will try to convey a few informations about 2 possible applications. One concerning data-driven and equation-informed tools for Eulerian turbulence. That is when you want to reconstruct space information, spatial informations, and the other about Lagrangian turbulence. That is when you want to reconstruct informations along some probe moving in your flow. So it's a sort of one-dimensional string of data. Just to give you an idea, I just played yesterday with a very popular by now tools. It is this DAL-E software that you provide a description, and the machine is suggesting you an image, and this is the very nice picture that I was able to realize just by asking the machine to produce a watercolor style image of a turbulent flow. This is the results, or a mirror style image of a turbulent flow, or a cubist style image of a turbulent flow. I mean, you see that the machines may have an imagination and a capacity to build up data in a very complex way. So this is just a sort of joke. Again, it's okay. So just the introduction to a quick 3-4 slides introduction to turbulent flows. I mean, typically, whenever we speak about complex fluids, you might have a very, very complicated equation of motions, very complicated situations. You typically have the advection, that is the Navier-Stokes equations, where you just describe F equal ma for a parcel of your fluid. And then on this backbone, that is the advection part of the Navier-Stokes equations, you also have in many situations, you might have this flow which is coupled with many other fields, many other applied cases. For instance, you might have the advection of temperature, and if temperature is advected, it might even react back on the fluid through the buoyancy. This G is the gravity term. You could have the flow that is conducting, and therefore you also have the magnetic field that is partially advected by the flow. And if the magnetic field is very intense, you also have the Lorentz force that might have a feedback on the velocity field itself. And in many situations, this would be of interest for us. You also have the fluid that is seeded with active or living particles. Could be small particles that are just transported and might break inside the flow. Could be animals, small animals, or could even be, Lagrangian objects, particles that are advected that might be active and intelligent, like, in the movie of many years ago, when people were imagined to have a very small submarine able to go and to move inside a complex flow. In this case, it was a cardiovascular, typical hemodynamic situation. And in many, if the particles are too many, the number of particles is large enough, the particles themselves might have a feedback of the flow, right? Because of the volume fraction, even simple volume fraction effects. And therefore, typically you have a situation where not only the backbone of your flow, but also all the added animals and players, the temperature, magnetic field, and other fields might interact, and the situation might become very, 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 very complicated. But main goal here is to convey to you today is that even in the simplest situation, that is when you don't have any other player except then the bare, simple, single-phase flow, that is the one described by Navier-Stokes equations, which is always there. I mean, any application will have this backbone. Then already in this case, there are many important open questions that are completely out of control from a theoretical point of view and also from a computational point of view. The important things to know is that in this case, in the backbone case, in the simplest case, you have only one control parameter that might change from one flow to another one, which is called the Reynolds number. It's a dimensionless parameter, and it simply tells you what is the ratio between the nonlinear term, the V grad V, so the quadratic term, and the dissipative forces. So in some sense, the Reynolds is just a measure of how nonlinear, how strong the nonlinearity are. And so, as you can imagine, we are interested in the system when it is strongly nonlinear. So when the evolution might become chaotic and very complicated. So we are in principle interested in the situation when the Reynolds number is very large. What happens? What are the problems when the Reynolds number, when you have this very simple flow and the Reynolds number is very large? What are the main open problems? Well, there are a few important problems that might be, if you want to summarize very quickly by two movies. I hope also the second one will start, even though I don't see it. How can I start it? Wow. We will see. So, I mean, that's too bad. It was running before. Anyhow, so I show the first movie here on the top. Let me just try to. Oh, sorry, the second movie doesn't start.
Maybe you can only play one at a time.
Yeah. Okay. That's. You think I can restart? You think it will work? Not clear.
Maybe if you pause the first one.
But I cannot pause it because I think this stupid laser pointer does not help too much. Okay. Okay. Anyhow, forget about the movies. I will jump this slide. This is anyhow only qualitative, and I will speak about the main problems by showing you some quantitative results. So the main problems when we have this turbulent flow at high Reynolds numbers are the following one. The first of all, the problem is multiscale. What we mean for multiscale is that, for instance, if you measure the energy spectrum of your flow, so how much energy you have at different wave numbers, and you measure it at changing Reynolds, so by increasing the degree of nonlinearity, then the system develops power law behavior. This is a log-log plot. So you tend to have a spectrum that follows a power law like K2 minus 5/3, and the larger the Reynolds is, and the more extended the power law becomes. What does it mean? It means the system is naturally multiscale. You have many, many wave numbers that are excited, and that in the limit, when Reynolds is very large, this range of scales where you see a power law becomes more and more extended. And it's very easy to make a really back of the envelope calculation to estimate how many degrees of freedom you have, degrees of freedom in the sense of dynamical degrees of freedom you have as a function of Reynolds, and they grow like Reynolds to 9/4. And if you imagine that a typical turbulent flow that you can encounter in the atmosphere easily reach Reynolds of the order of 10 to the 7, 10 to the 8, immediately you realize that the number of degrees of freedom that are at play in a turbulent flow are enormous, astronomically large. The first problem is that the multiscale, you have many, many degrees of freedom, in some sense, infinite number of degrees of freedom. The second problem that makes the system hard is that if you make a cut inside your turbulent flow and you measure, for instance, a profile of the velocity field, you discover that the profile of the velocity field is only order continuous. So it's not differentiable. If you measure the velocity difference across a distance r, it does not grow linearly with r, but grows like a power of r to the 1/3. And this means that if you cannot differentiate, right? If you divide by r and you send r to 0, you would have something that goes to infinite. So the system is very rough, and you might have oscillations and fluctuations of your velocity field that are extremely difficult to predict because they are never differentiable or linearly interpolable. The third reason why the system is tough is not only that it's multiscale, not only that this multiscale produce rough velocity configurations of your velocity field, but on top of that is also strongly non-Gaussian. For instance, here I show you the PDF of the velocity increments at a given distance r, normalized with its standard deviation. So this is simply, the PDF of the PDF of the distance between two or the difference between two velocities at a given distance r, and by changing the distance r, and then I show the PDF normalized with the standard deviation and at a different distance. And by going up in these curves, you have distance that becomes smaller and smaller. And you see that the PDF this is a log linear plot. The PDF is strongly non-Gaussian. A Gaussian would be a parabola, and this is true for very large r. But when you go to scales that are smaller and smaller, the PDF becomes strongly and strongly non-Gaussian. And the degree of non-Gaussianity is extremely high. I mean, you see that here you have the variable normalized with its standard deviation. You may easily measure fluctuations that are 40 times, 50 times the standard deviation. So this is really a wild phenomena where you have the probability to observe extremely intense event, which is small, but not astronomically small, as you would have in a Gaussian distribution. So the system is multiscale, is rough, and on top of that is strongly non-Gaussian. And typically, if you want to visualize these strong events, I show here the evolution of the velocity along one particle trajectory advected by the flow, and you see that from time to time the particle enters in. I mean, typically they fluctuate in a more or less mild way, but then from time to time they enters in very small tornadoes where the velocity starts to fluctuate with intensity that is extremely large. So these are the three main ingredients. The equations of motions, even when you look only at the backbone, which is always present, I repeat, in any possible application, then the equation of motions have almost infinite number of degrees of freedom, rough fields, and strongly non-Gaussian fluctuations. As a matter of fact, at the moment, nobody is able to predict, starting from the equation of motion, the statistics of a turbulent flow. We don't have any way, any analytical way, any systematic way to predict the kind of a PDF that I was showing you before. All these measurements are empirical measurements, either from experiments or from direct numerical simulation. We have almost no analytical control on the system. So this is the motivation, and typically you see it might be very, because you have big data anyhow. I mean, the flow is made of a very large and big amount of degrees of freedom. It might be interesting to know, and because you don't have any analytical real tool to control the statistics and the behavior of this system, it might be interesting to see how much these tools based on data-driven and machine learning application might be applicable to problems like this. So let me skip a little bit the possible application. I mean, we have application to dispersion of particles in turbulent flows. We have application about rotating flows, application about sheared turbulence or magnetodynamic turbulence. But I mean, this is not so important at the moment. Let me give you a few ideas about how and what are the most interesting questions, at least up to me, that one might ask in this data-driven game. Well, one question is the one that I was discussing at the very beginning, at the very first slide. Now we have, it's a question concerning data augmentation and understanding on the quality and quantity of data that you need to reconstruct a turbulent configuration in a systematic way. So the typical problem that you would like to understand is the following. You have some configuration of your flow, which might be very complicated with a lot of degrees of freedom, and you suppose that you miss some information, right? Information could be just because you cannot measure everything. You have some spots that are blind in your camera. Could be because you have sensors that are not efficient. I mean, for many different reasons. The question is, how much I can reconstruct. I mean, how much I can, on the basis of the data that I have, I can reconstruct the missing information. This is important for two main reasons. First, because you might have an applied problem. I mean, this could be a cloud, right? You can really have the problem that you don't measure something and you want to reconstruct. But then, and this is the reasons that is more motivating from my point of view. The second one is that you might use this kind of reconstruction games to ask questions about the physics. I mean, because you can ask, is it more important to have information or to miss information close to the boundary or in the bulk? It is better to have maybe only a few spots that are missing, but with the same total area of a case where you have small spots but much more dispersed to reconstruct or not. I mean, in this way, you ask indirectly questions about the quality and the quantity of information that you need. And this is a very important question in systems like in turbulent flows, where you have many, many degrees of freedom, and it's very difficult to have building bricks. Nobody knows what are the eigenfunctions in a statistical sense of our turbulent flows. So it's very important to have questions that might ask directly by looking at the data, where it is important to measure, or where it is important to not measure in order to accomplish some task. So the typical question that you can ask in these games are, as I say, it's better to input spatial or temporal data. I mean, it's better to measure in one configuration or along something that is moving. How many variables do I need to reconstruct the information, right? Again, if the flow would be linearly interpolable, linearly smooth, well, then probably to reconstruct the information is not so difficult, right? On the other hand, we know that it's rough and it's strongly non-Gaussian. So even a prior that is just based on replacing what you miss by statistical Gaussian tools, it might be strongly it might fail blatantly. And then there are many other questions. I mean, as I said, I mean, you can ask questions about what happens when you remove information on the boundaries, on the bulk, if you do it on scale-wise, right? So if you remove information not in the space, but in Fourier space. so not in configurational space, but in Fourier space. So you ask about super resolution, blurred images and things like that, and you want to understand if you can guess what you have missing in terms of what you are measuring. So they can, just to be specific, I show you a couple of applications. For instance, this is a very typical application that you have in satellite image reconstructions. So you're supposed to have a satellite image, for instance, of the surface of your ocean, right? And that there is a cloud. Well, in this case, it's a squared cloud, but it could be any, this is a random cloud on the other end. So you have a part of your field view that is obscured and you cannot measure. And you would like to understand how much you can guess, how much you can reconstruct about the missing region. And so this is the ground truth, if you want. And then these are two possible realistic situations where you have a random pixel or damaged, or where you have a big gap inside your field of view, and you would like to, and maybe the gap is larger and larger, and or the percentage of random damage is larger and larger, and then you would like to understand how much you can reconstruct, knowing that the flow, the underlying flow is highly non-Gaussian and multiscale and so on and so forth. We played a little bit systematically with these kind of questions, and we applied mainly 3 different approaches. 2 approaches are completely data-driven. So they are approaches where I do not know anything about the equation of motion. This is just one image, like it could be the face of a Hollywood star, and which is damaged, and they want to reconstruct the face. Here I want to reconstruct the turbulent configuration. So 2 approaches are completely data-driven, and the difference between the 2 approaches is that one is data-driven, but using a network, a machine that is just a fully nonlinear, millions of degrees of freedom of free parameters to try to guess what you miss. And another one is more standard, it's just based on a linear decomposition using some eigenfunctions that you can extract from your data. So we have 2 tools that are completely data-driven, one linear, one fully nonlinear. And then we compare them with a tool that is on the other end, fully equation-based. So when we know the equation of motions, so we know the physics that is behind the flow that has that is behind the image that we are analyzing. And then, if I have time, I will also say a few words about the tools that try to combine the 2. These are the so-called physics-informed machine learning tools. That is when you have a data-driven approach, but where you try to fix some constraints on the basis of the physics that you know. Just to give you an idea, the newest application is the one, as you can imagine, based on fully data-driven neural network approach. Well, then there are many different possibilities to solve the problem. I'll give you the one that, according to me, is the most powerful, and it is based on the idea that in order to reconstruct correctly, so you have some input data that is damaged. It has a big gap, and you want to guess what to put in the place of your gap, right? And the idea is that if you want to do that, you cannot do it only based on a sort of energetic requirements. I mean, you cannot simply ask to be compliant in a L2 norm sense with your ground truth. You also need to know what is the statistics, because, as I said before, when you have a PDF like this that are strongly non-Gaussian, it's not enough only to guess the standard deviation, if you want. And then once you know the standard deviation, you know that it's almost Gaussian, you can refill more or less in a systematic way. It's very important to have the whole shape and to be able to control not only the mean squared error, if you want, but to control also the physics with all possible events more or less extreme. So, and the idea of this, how to invent machines that are sensitive to both, to the statistical PDF and to the mean square error, it's typically done in an adversarial way. So people use this generative adversarial network. What is the idea? The idea is that you have first a machine that is just trying to produce a guess of what you miss by minimizing the mean square error. So just by minimizing the distance, the L2 distance between the ground truth and what you predict. These are all, of course, all supervised learning. So I must have a set of configurations where I know the ground truth. So first I have a machine that is just doing the blind attempt to reduce the L2 norm, the L2 distance. But if I do that, I might, and as I will show you later, the results might be very poor. Why it might be very poor? For the reasons I was saying before. I mean, maybe you reduce the L2 norm with a stupid Gaussian distribution, but the statistics is completely non-Gaussian. So it's of course wrong. So what people do, they do not only have this actor, so this machine that produce a guess, but also they have a critic. So they have another machine that is trained simultaneously to the actor to discriminate if what you produce is good or not. So this machine is simply a sort of binary machine that tells you, yes, it is good concerning the statistics, or no, it's bad concerning the statistical probability of the flow. So it's a machine that is trained by using as an input the output of the generator and simultaneously the ground truth, so the statistics that is the real one. And then you combine the costs of the two machines such that the first one is trying to produce something which is producing something which is realistic. And what do you mean? What do I mean for realistic? Is something that is confusing the discriminator. Right? So if you are able to have this generator that produce images that are undistinguishable from the discriminator, and if at the same time you are able to train the discriminator to be very good in discriminating, in some sense you are training the discriminator to be a good critic and training the actor to be a good actor at the same time. And this adversarial game, it is played in a systematic way with suitable protocols to minimize the two costs, and in a way that at the end you reach an equilibrium. The generator is able to produce something that is good. The discriminator is able to discriminate, but because this is good, the discriminator will not be able to distinguish. So in some sense, we produce a machine that is able to produce to generate turbulent configuration that are undistinguishable from the ground truth by another machine. So it's a game only played by the machine themselves. There is a question, please, Dina.
Yeah, this is very interesting, and I want to understand it a bit more. So I understand what you are doing when you minimize the distance. Yes. I think there you minimize this is the minimization of the
L2 norm, of L2 distance, yes.
Yes. Now I'm not sure I fully understand the discriminator.
The discriminator works in this way. I can say a few words more. The discriminator works in this way. The cost that the discriminator is trying to minimize is given by this cost function. And it's a cost function that is made of two terms. D is the output of the discriminator. The discriminator, it just gives you one number, 0, 1. If it is 0, it tells you that according to him or to her, the configuration is fake. If it is 1, according to him or to her, the configuration is good. Right? And then you try to train the discriminator in this way. You take the log of the output when you give the right information. Right? So if it gives you D equal 1 is maximize, okay, there is a minus, sorry, in front of this. So when you give when you give the right configuration, it gives you 1, right? 1 is the maximum of the log. So because there is a minus in front, when you give the right configuration, if he is able to give 1, you have minimized this cost. And on the other hand, when you give the output of the generator, the function that is trying to minimize is log of 1 minus D. Right? So again, if he is able to discriminate, he will give a 0 to the fake, which is again minimizing this quantity, right? But so is the discriminator, it will try to balance the cost function in this two way, right? On the other hand, you see, if the generator is able to produce something that the guy does not discriminate, then even you predicted it will be very close to the U-truth, and this will go in between and give you log of 1/2, log of, plus log of 1/2. So there is, I don't know if I explained myself, there is a balancing between the two contributions. Does it clarify a little bit?
Yeah, okay, I get the idea, yes. Thank you.
So, so what is important to understand, nevertheless, is that the generator generates the whole configuration, and this is just a yes/no. It's just telling you, okay, it's good, it's okay, it's bad.
Okay.
If you do like that, and then you try, okay, now I don't want to enter into details of the network, and then, okay, there is also another way to construct, but I will skip it. If you do like that, and then you need to train, right? This is very important message for people that wants to apply these tools. What does it mean to train? It means that you need to provide hundreds of thousands of this configuration in order to allow the machine that has millions of free parameters to be tuned, in order to allow the machines to converge.
Okay, Luca, here I have one question.
Yes.
Do we know quantitatively or approximately how the number of data that we have to fit in are related to the number of parameters?
I will come back to that. This is a very important question. Of course, I will come back to that. It is a big issue. Okay. And for the moment, let me say, frankly, no, we don't know. Right? So certainly you cannot do it with 10 configurations, let's say. But I mean, typically, for instance, in the game that we are playing now, that I'm going to show you, we needed to use order 80,000 images for the training. And when you train with, so you supply these images many times and you train. So each epoch is one training on a slot of 80,000 images. And then you see there are 60 epochs training. Then slowly you see that the total cost is decreasing. It means that you learn how to refill better and better. Here I show you, for instance, how much you can refill by taking different epochs during the training. You see at the beginning you refill very badly. In the middle you have improved a little bit. At the end you have refilled with something that at least by eyes looks reasonable. So these kind of things are really data. They need a lot of data. That's for sure. But then the question is, apparently it seems you have refilled well. Then the real question for a physicist is, how do I benchmark? I mean, how do I know that this is optimal and in which sense? So typically what you need is also some other tools that are based on other approaches and that use the same data, of course. I mean, you must play the game in the correct way, using the same quantity of information, and you want to compare. So one possible way to compare is using what people call proper or principal orthogonal decomposition. What it means is this a linear way to guess eigenfunctions that you can use to reconstruct your field. The idea is very simple. It is very old also. And the idea is simply that you have your database, you estimate the correlation, the 2-point correlation of your field, of the field that you want to reconstruct on the whole image, because it's supervised. So you must imagine to have the whole field for at least 80,000, 100,000 configurations. So you measure the correlation, then you diagonalize this symmetric tensor. So you have a set of orthonormal eigenfunctions and eigenvalues, and you can use these eigenfunctions as a basis to decompose any velocity field in your ensemble, right? So the point is that what is the problem? The problem is that when you have a gap, you cannot invert the decomposition, because to invert the decomposition, you have to do the scalar product of the eigenfunctions with your images, and therefore you need to have tools to find what is the optimal set of coefficients that you must use to reconstruct the field also inside. So it's the inversion is not possible in a rigorous way. when it is easy to do? Well, it is easy to do when the flow when you have the data, the flow is very simple, because then you guess that you can reconstruct the field with a few coefficients. So it's only, you need only to guess a few and to optimize a few coefficients to reconstruct. But when the flow is very complex, as it is a turbulent flow, you know that you need thousands of coefficients to reconstruct the whole flow. And therefore, I mean, independently of how much information you have in the framework, it might be very difficult, if not impossible, to invert exactly in a one-to-one correspondency the linear decomposition, and so to guess the right coefficients. And so what happens is that then you need to find the optimal set of parameters. I don't want to enter into details, but I mean, the idea is simply that you need to find an optimal number of coefficients that might be used to reconstruct the flow inside your gap on the basis of the linear decomposition that you can extract from the data that you have. If you do like that, here I show you some results, which is, I think, instructive. I compare the mean square error, so it's just the distance. Now, I take either the machine, the generative adversarial network, I have trained it, then I freeze it, right? So I mean, I reached a minimum of, I freeze all coefficients. So I have my machine that is trained, and then I try to see, and I validate my training on a set of different configuration. I must use different configuration that has never seen during the training, otherwise there is the risk of overfitting, to validate how good the training was. So now I freeze my network. I have on the other end also simultaneously found these eigenfunctions. And then I try to optimize the coefficients in the linear decomposition in order to refill the gap. And I compare with what I obtain when I use the network. If I compare the results in terms of the L2 norm, here is the mean square error as a function of the size of the gap. Here it's a relative size. 1, it means that I almost emptied everything. I only kept one layer in the framework. 0.5, it means that I have a gap that is whose size is 1/2 of the total size of my image. Here I compare my machine, my nonlinear GAN, the generated adversarial network, with two different linear decomposition. I mean, I don't want to enter into the details of why, but these are two different linear proper orthogonal decomposition. And you see that the GAN, the machine, it has a mean square error that is pretty small, becomes large, which is 20% anyhow. This is a normalized, sorry, I didn't write, it's normalized with the total energy. So it's, when you see 0.2, it means that in average, I make a 20% error. You see that it's the mean square error is pretty small, but it's not that smaller than one linear decomposition. And if you want, you can see also in this example. Here it's one example of the original damage. On the right, you have the ground truth. These are the two linear interpolators, and this is the nonlinear machine. You see that the nonlinear machine is not that bad with respect to the original, but even one of the two linear tools is not so bad. I mean, the first one is always very bad. So what is the message? The message is that if you look only at the L2 norm, the nonlinear millions of free parameters neural network is not that bad, but it's not superior to tools that we had since 30 years ago. And I doubt one can do much better by using other networks. On the other hand, the big difference, you see it when you look at the PDF, when you look at the statistics, when you look at the physics. When you look at the PDF, here I show you the results. For this is, for instance, the PDF of the velocity field in the image. The black line is the ground truth. And the symbols are the PDF of the network, of the neural network, for 3 different sizes, 1/3, more than 1/2, almost 1. And you see that the network is able to reproduce the whole statistics very closely. By the way, this was the amplitude of the velocity field. That's why you see only positive values. On the other hand, the two linear tools, one of the two is very bad. The other is not that bad. It's close to the ground truth. That is the black line, but certainly is not as close as the machine. You might want to quantify these. You can measure, for instance, the Jensen-Shannon distance between the two PDF. It's just a matrix that tells you how much the two PDFs are different. And when you measure this distance, you clearly see that the nonlinear machine, the GAN, is at least 1 order of magnitude better in the distance with respect to the two partial linear interpolators.
Luca, can I ask something?
Yes, sure.
Regarding the cost, how is this airport compared to the GAN, and how does it scale? I mean, this.
I'll comment about that also. I'll comment about that.
Okay, sorry.
The improvement of the GAN with respect to the linear interpolators, it's even larger if you look at the gradients. So if you look at the small scales, but this maybe I will skip this slide. It is easy to understand. I mean, if the GAN is able to really capture the complexity of the multiscale physics, then when you look at the gradients, you are enhancing the small scales, and therefore you are it's normal that is even better than the linear interpolators. Let me, before going to your questions, Dina, let me just present shortly a completely different point of view. That is the one equation-based. So now we suppose to know the equations. So we know that the image has been produced by our Navier-Stokes equations. How can I use the data that I measure to refill the gap by using the equations? Well, one way is to use this tool that is called, by the community working on numerical weather forecast, nudging. What is nudging? It's a very simple idea. The idea is to say, okay, I know the equation. I know that I have some measurements here. What I do, I run my numerical simulation of the full equation by adding a term that is a linear penalization against my data. So I just add a term that is, you see, a Newtonian relaxation. My data are Vn. I call Vn the data that I have on the framework, and I simply force the equation to be close to the data where I have the data. It's natural. What happens? It happens now that you see, even with only one frame, here there is no training, right? It's enough to have one frame, and then you can ask Navier-Stokes equations to evolve around this frame, trying to be as close as possible to the frame. But because Navier-Stokes equations are evolved in the whole volume, they will refill also what you have in the square. And if you are in 3D, they will refill also the whole three-dimensional volume. What is the big advantage and the big disadvantage? Well, the big advantage is that here you don't need the training. You don't need hundreds of thousands of configurations, because Navier-Stokes, the guy that have discovered the equations, gave you the right ensemble, the right physics, right? What is the big disadvantage? The big disadvantage is that to do a simulation like this in 3D, it takes 100 millions of core hours in a big supercomputer. So it's on one side, the machine needs a lot of data as input, but then once you have trained it, you supply one image and gives you the output in 1 picosecond. The equation-based tools is exactly the opposite. Does not need any data in input, except the one that you want to reconstruct. You don't need any training, but in order to guess what you feel, you need to evolve the full equations, which means to perform a direct numerical simulation of a system that has billions of degrees of freedom. So it takes typically 100 millions or 10 millions of core hours on a supercomputer. So these two approaches are really the opposite of the others, right? One is very good if you have a lot of data, but you don't know anything about the equations. The second is very good if you know the equation, but you don't have a lot of data in input. Recently, people have started to apply and to try to combine the two. with this physics-informed machine learning approach, which is very promising in principle. At the moment, it has been applied to very simple situations, so it's difficult to say if it is useful or not. What is the idea? Which is very nice, I think. The idea is the following one. You have a machine, right? So suppose this is an application which is very easy to understand. Suppose you have particles that go around in your two-dimensional flow. This is a two-dimensional flow. And that particles, and you have a collection of, you measure things only where the particles are, right? So you have what? You have a sparse data on X, Y, and T, right? You at different times where the positions, where the particles are, you have, for instance, you measure the concentration, the temperature, the concentration, the temperature of the flow, right? Or the concentration of a dye, of a color. So you have these sparse measurements, which is very open, happens very often, for instance, in geophysical applications. So imagine the drifters and buoys that go around in the ocean. So you have only sparse localized measurements in time and space. Then you want to reconstruct the whole flow around you. How do? You use still a machine. And you want to do it using the equation of motion also, helping with the equation of motion. You still use a machine. In input, you give the position where you have the measurements, which means time and positions where you have the measurements. And at the machine, you ask to produce with these 1 million free parameters, a fit for what you measure, the concentration, and also the other fields, the velocity, horizontal and vertical velocity fields, and the pressure, that enters in the equation of motion, because you know that the Navier-Stokes equations, they have the velocity field, the pressure, and the concentration if you want to evolve the real system. So then what you do, which cost you use to introduce physics-informed machine learning? Well, you try to minimize a cost, which is the distance between what you measure, the concentration, and what the machine produces, right? So here you use your field measurements. You have the temperature, and then you want that the temperature produced during the training by the network is the same of the temperature that you have measured. But then you add a cost, which depends on how far the fields that you produce are from the real Navier-Stokes equations. So what you have, if you have the concentration, horizontal, vertical, and velocity and pressure, you can back differentiate. So you can, these are functions of t, x, and y. So you can estimate the time derivative and the spatial derivatives. And if you have an estimate of the spatial derivatives and time derivatives, you can reconstruct the equation of motion. So you can see how much your output is. If you have the equation of motion that are satisfied, this quantity would be 0. This quantity would be 0, this quantity would be 0. The divergence would be 0 because the field is divergenceless. So what you do, you add a cost, which is how far your output is from satisfying exactly the equation of motion. So you have a physics constraint based on the equation of motion that force the machine not only to produce C, U, V, and P statistically correct, but also spatially and temporally correct. Connected with the structure of your equation of motion. Does this tool, of course, this is very important because it forces the machine to be physics compliant, right? Does it work? Well, we don't know. In the sense that we know that it works well for very simple flow, for instance, for flow that are not rough, so they have not this problem of Odor continuity only, for flow that are not strongly non-Gaussian, and we still do not know how well it works, and if it works for flows that have a realistic real interest. But the idea is very promising. In the last 5 minutes, I give you, because I promised at the beginning also, an idea of what you can do data-driven for instance, a Lagrangian problem, where you want to control what you do when you move inside the flow. So typically, just give you an example, because it's a little bit prototypical. This is the Zermelo problem. What is the Zermelo problem? The Zermelo problem is navigating from point A to point B in the shortest possible time. What it means? It means that you suppose that you have a boat. The boat has a velocity, which is the one of the flow underlying the boat, plus a control. So you have an engine that you can switch on and off. And the control, you see, it's an intensity times averso. So you always have the engine at the same speed, and you just can decide where to steer. You want to go the right, left, top, down. Of course, the problem is trivial if the velocity of swimming, if the velocity of your engine is very large, because then you don't see the flow underlying you and you go straight. The problem is impossible if the velocity of swimming is at 0, because you go where the flow brings you. So there is no reason why the flow should bring you from A to B. For velocity of your engine that is in between, the problem is a problem of optimization, minimization of the arrival time, highly non-trivial. Why is highly non-trivial? Because the flow underlying you is a chaotic flow that has a very strong, very difficult, very complex evolution in space and time. How do you attack this kind of problem? This type of problem that depends on what you do, right? You try to optimize actions, and depends on what you do. They are typically attacked with a reinforcement learning approach. What is a reinforcement learning is just a data-driven approach where you have trials and errors. So you decide, you have a sort of possible actions. For instance, steering in these 8 possible directions, and you need to decide which action to take depending when you are. And you want to find an optimal policy that tells you, okay, I am here. To reach the target, it's better to steer in one direction or to steer in another direction. How to find this optimal policy? You can find it by using these reinforcement learning techniques. These are sort of trial and error. It's why it's a reinforcement learning, because you go around, you try to do something. If you do the right things, you keep a memory of the action that was good. If you do something that brings you away, then you keep a memory that that action must be penalized. And in this way, with trial and error and with a suitable protocol, you can try to converge to an optimal policy. An optimal policy, which simply means mapping where you are, what to do in order to reach the target. And this, again, you can do it, well, you can do it with optimal control in principle, which is completely equation-based. I will tell you a few words. You can do it in a heuristic way. For instance, one could imagine that the best action is just to steer in the direction of the target, right? But of course, this is not true, because sometimes you might want to use the flow to bring you across a region that might swing you in the right direction, right? Like you do with lunar orbiters when you want to send them to Mars, satellites. You want to send them to Mars. Sometimes you pass through the moon to take advantage of the swing effect of the moon, of the gravitational effects of the moon. So here you can do it the same, but here the problem is that it's not a moon or planets. Here you have a flow that is moving around you in a very complex way. You do these things, and just to give you an idea, a visual idea of what you can perform, you can, oops, no, if the movie does not work, this is too bad. Wow, that's a big deception. Let me see if I can quickly exit. No, it's a mess. Do you see the screen? No, right?
We do, but not the presentation.
Which screen? Okay, you don't see the presentation. Now you should see this. Do you see the presentation?
Yes, maybe if you play it now, it will work.
now it should work. Yes. So I'll give you just a very quick. This is I compare the policy that I got by using this reinforcement learning. These are the blue policies. So I just once I optimize, I throw 100 particles following that policy, going from A to B with the reinforcement learning, and I compare these policies with what I would obtain just by using the naive policy to always swim in the direction of the target. And you see that the reinforcement learning is clearly much better to reach the target, first of all, quicker, and second, in a much more robust way, because you have much less dispersion. Just to give you an idea of how much these data-driven tools might be helpful when you see the flow underlying you is highly complicated. It evolves in a very chaotic way. So let me just go now to the conclusion to comment a few. I can go again, maybe like this, to comment a few points that were raised by. Do you see the screen? Hello?
Yes, yes,
okay.
we can.
Yes,
Okay, so just comment a few points that were raised by.
Hold on, the window is in front of the.
Yeah, that's. But I don't know how to remove. Okay, wait. There is this problem of. Wait.
Put it in front. We can see it without presentation mode. It's fine.
But now I don't know how to put in front anymore. I cannot. Okay. It's a mess. Huh?
It's fine.
Do you see something or not?
We see the iMac controls. Yeah.
Yeah, which is
not
very
the
good.
PowerPoint.
Okay, it is.
Now, yeah.
Okay.
If you make that bigger, it'll be fine.
If I make it bigger, okay, now it works. Sorry for the mess. And so just a few take-home message that allows me to answer some of the questions by Dina. So certainly these data-driven tools might be useful also for a community that is data hungry, like the one of computational fluid dynamics. And they certainly are better than other linear tools. I mean, this is not surprising. I mean, non-linear things should always be better in some sense. There is, nevertheless, there might be a big trade-off when we use physics. I mean, it's highly non-trivial to understand how much important it is to supply information about the equation of motion. At the moment, we have too few cases to understand if indeed when the equations are complicated as the Navier-Stokes equations, you might indeed use them in a useful way for data-driven tools. What is always very important is to compare against baselines, because the fact that you get a result is not clear that it's better than something else that could maybe achieved with less effort. This about backpropagation I didn't say. There are two main problems that are connected to what Dina was asking. The first problem about the data-driven tools is the interpretability. I mean, typically it's very difficult to go, once you train some machine and you get something that works apparently very good, it's very difficult to understand why. So it's very difficult to understand what you learn indeed, except for the fact that you have a tool that is useful, right? And the kind of question that I was asking at the beginning, I mean, you know, changing the amount of data that you remove, changing the kind of information that you give, it's a first way to rank, right, the features, the data that you give, but still is not to go inside the machine and to understand which kind of operation the machine has learned to refill the gap. It's very difficult to do. It's very difficult to do indeed. The second problem that we miss completely is the second question by Dina, is the dimensionalization of the machine. I mean, just to say it frankly, you give me some data set and you tell me, can you at least guess a priori how many free hyperparameters you need to use in your network to get good training and the good results? It's impossible. I mean, it's very difficult to guess this. I mean, we have no way to, you know, given the complexity of the physics, guessing what is the complexity of the machine that we must use, which is very upsetting, especially for computational people, right? I mean, if you ask me to do a numerical simulation of a Navier-Stokes equation or of a lattice gauge configuration at a given temperature, I can give you almost precisely what is the size, the size of the lattice, what is the size of the time step that I have to use. I mean, I know how to translate the complexity of the physics with the complexity of my numerical tool. Here, it's really black box. You need to try to change the hyperparameters, to decrease a factor 10, and to increase a factor 10. And even worse, it's very little transferable. I mean, if you train a machine on a given physics, and then, you know, you want to upscale, just having a physics that is slightly more complex, then, of course, you can use the machine that you have already trained to start a new training. But it's, I mean, if the two cases are far apart enough, then it's almost useless. I mean, it's like if you have to start the training again from scratch, which might mean weeks and weeks of, you know, training on tens and tens of GPUs. So this lack of transferability, difficulty of interpretability, right, and the difficulty to dimensionalize, it's, I think, the main big problem for our community. And my final take-home message is we need to all costs avoid the too big jumps. I mean, in the literature now you find people that, you know, train the model on a stupid Lorentz 96 dynamical system, which is you know, a ODE with 45 degrees of freedom. And once the model works in a stupid ODE with 45 degrees of freedom, you take it and you apply blindly to, I don't know, a model of the global circulation in the atmosphere with 15 different physical fields and billions of degrees of freedom. This is, I think, very, 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 very risky. And with this very simple and stupid statement, I think I can stop here and take your questions. Thank you.
Thank you very much, Professor Virai. Now question time. Panayoda, you have your hands raised.
Hello, and very nice to meet you. Thank you as a fluid dynamicist. I found this a fascinating talk. Just to clarify, a question to clarify, did you train across different Reynolds numbers, or is the training that you do is for a given fixed Reynolds number?
In the case that I show you, it was for a given fixed Reynolds number. We tried also, and we did it with a different Reynolds number. Then it's good to label, if you want to refill, to label it. So to tell the machine once you have trained that he needs to refill with that particular Reynolds number. So this will help a lot, instead of asking the machine to discover from the framework what is the Reynolds number. I don't know if I explained myself.
Okay, thank you very much.
When you train with different Reynolds number, you can do it in two different ways, right? Telling the machine, okay, I give you Reynolds 10, or I give you Reynolds 50 and produce something, or you cannot say anything, and hoping that the machine is able to understand from the frame, right, what is the Reynolds of the flow. Of course, this is much more difficult.
Thank you very much.
Yanni, please, your question.
Yes, hello. Thank you very much for your presentation. I have a question about one of your introductory slides, and where you discussed that due to the high Reynolds number of the system that you're studying, then your system is multiscale, and then essentially you have very high fluctuations.
Yes.
So, there is a high need to perform this data-driven methodology. So my question is, when the Reynolds number is much lower, then I guess the system has a high energy dissipation because the viscosity is quite significant.
Yes.
Then in that case, is there still a high need to perform this data-driven methodology, or as your system is not, we can say, multiscale?
Yeah, well, this is a good question. I guess that maybe you might still have a small Reynolds, but the system might be very complicated for other reasons. For instance, if you have a multi-phase, right, you may have many different bubbles with different size. Think to a foam or an emulsion, where you have the system is almost velocity is almost at zero, but the interface of the bubbles and of droplets is very complicated. And then you need then it's like to have a texture and in the image that is 0, 1, 0, 1, but still with the texture that is very complicated. And then it may be difficult for a linear system to have a good reconstruction. On the other hand, I fully agree with you. If the flow is not multiscale and there are no other big issues, then a linear interpolator like a principal orthogonal decomposition, it will already work very well. Why? Because the principal orthogonal decomposition is just minimizing the norm of the L2 norm, which is just one, the mean square error. So it's just, in some sense, a measure of your energetic content in your configuration. So it's if the flow is smooth, it's enough to guess the right fluctuations, and then you will it will not have many degrees of freedom, and therefore, I mean, any linear decomposition, if clever enough, it will work pretty well. So when Reynolds is not high, I think the main reason of using data-driven tools is when you have other complexities. It might be, I mean, as I said, the texture of the surface.
Okay. And just a question, general about fluid mechanics, because I have forgotten lots of things about fluid dynamics. So when we have a high viscosity in our system, this also implies that vorticity is higher or not?
No, it depends. I mean, it's not, as I said, it's not high viscosity, it's the Reynolds number, which is important. Reynolds number is a dimensionless parameter that is here. It's just that you see, it's the ratio of viscosity enters, of course, right? So it is typically the typical velocity of the flow, the typical size of the flow divided the viscosity. So if the geometry is the same, so V0 and V0 and L0 is the same, then high viscosity means a small Reynolds, so laminar or simple flow, and small viscosity means high Reynolds, and high Reynolds means high vorticity. Because vorticity is a gradient. Because vorticity is a gradient. So vorticity is very sensitive to small scales. So only if you have a multi-scale system, vorticity will be high, because you are measuring a gradient.
All right. Okay. Thanks a lot.
Thank you, Yanni. Vangeli, your question, please.
Hello, Luca. Thank you very much. This was very interesting. Actually, my question was more or less a follow-up, let's say, from Yannis. I was thinking about, as you mentioned, most of these cases refer, let's say, to rather simple flows. So I was thinking, when you have spatial heterogeneities, when you have interfaces, as you mentioned, when you have multi-component systems, do we have any indication about the scalability of the methods and how well, let's say, might work for such systems?
Yeah, I mean, I think that the main issue is not really, you may have complex flows or complex fluids, or complex flows and complex fluids, as I say, by the way, in this slide, right?
Yeah, I was thinking for the latter case, complex flows, complex fluids.
Exactly. So here, here I show, in some sense, simple fluids because it's single phase, but complex flows, right? It's turbulent. Then you might have, on the other hand, you might have a simple flow, which means, a microfluidic case where the flow is almost laminar, it's very predictable, but the fluid is complex because you have droplets, bubbles, and some. So the real control parameter is the degree of complexity, in some sense. So how many degrees of freedom you need to characterize your environment. And what is, I think, even more important, if these degrees of freedom are very heterogeneous. So it might be some are Gaussian, some are strongly non-Gaussian, some are small scale, some other are large scales. So it's the complexity is more in the heterogeneity of your environment than on the kind of degrees of freedom that you deal with.
Exactly. So the question is, when you have such heterogeneities, let's say strong heterogeneities in the system, is there any indication how much more data or whether these methods can be applied? That's my question. Let's say that you have PDFs over high dimensional space.
Yeah, I mean, typically, yes. I mean, that's, these data-driven tools are, of course, idealized, if you want, when you have high dimensions. So it's yeah, yes, but nevertheless with the warning that I mean it's very easy to go out of control, in the sense that if dimensions are too large, then it's difficult to have enough data. I mean that's. I mean there is a big risk of hyperfitting.
Sure, yeah.
because you use billions of data to train the model, and it's important really that then when you validate it in a robust way by being as far as possible from what you have used for training.
Due to the overfitting you might have.
Yes. Yeah.
Yeah. Good. Thanks. Thank you very much.
Thank you, Vangeli. Is there any other questions for our speaker, please?
Dina is raising her hand.
Professor Alexandru, do you have any questions further?
We cannot hear you. I cannot hear you.
Sorry. Look, this is fascinating. Thank you very much. I mean, intuitively, these physics-based approaches are the most appealing for physicists, because you think that if you put information, the training should be faster and more accurate, right?
Yeah.
Now, you said that this is still limited to simple systems, and I think that's the problem we see everywhere, also in the things that we are trying to do. We cannot scale up. What do you think? I mean, what do you think is the problem there? I mean, to really scale these methods.
Okay.
Okay,
this is a question that I don't know how to answer. I can tell you my feeling. The problem is that we have not been able yet to convince the community working on the development of this kind of software that we have interesting problems. In the sense that, I mean, what is the main drawback of this application? The main drawback of this application is that it's impossible to develop by ourselves the algorithms. I mean, you must cherry pick what these big software companies or AI companies give you. I mean, it could be OpenAI, it could be Google Team, it could be Microsoft, whatever. So you can of course make small adjustments on the algorithms, but the infrastructure is there. Now, I mean, the community of biophysics convinced them that the problem of guessing the protein folding was an important problem, and they solve it.
Exactly.
They invest enough human capital and computational power to solve it. But it takes, it's not something that you do it, on your cluster. It's something that you need the equivalent of hundreds of millions of euros of investment in solving that problem. So I think this was one of my points of my take-home message. It's very important that our community try to fix clear, quantitative, important benchmarks or grand challenges, and then slowly, the community will build on that and converge toward these problems. But if we on the other end, we continue to do as we also did, to cherry pick some problem that is your preferred because you have some feeling, you have some data, you know that it might be interesting for you, and then you just in some sense show a proof of concept, but we do not build grand challenges, then it is very difficult to progress. My feeling is that, I mean, we are just following what the others do. So when you say what is the difficulty to upscale? The difficulty to upscale is to make a case. I think, because if you make a case, then probably the community does already know how to upscale, but it's not something that can be done by me or by you. It's something that needs, the community of people, software engineers working on the field, of the guy that develops the hardware. I mean, it's something that is still in development. It's not only that we have the fast Fourier transform, we just need a bigger and bigger computer to increase the resolution. It's really is as if we need something else than fast Fourier transform, and we need to develop it. And it's it's not you that can do that, you see.
Yeah, so exactly. So yeah, and this is an interesting discussion. What kind of research groups you can build if you identify this problem that could really go after and solve it, right?
Yeah, I mean, first you want us to understand if you have the problem, because not all communities have problems that are equivalent to the protein folding, right? I mean, there it's clear that it's an important problem. There are tons of experimental data, numerical data. It's clearly an important biological question. So it's, the interest of the problem was clear. So it's not obvious that the other communities like yours or mine have similar problems, right? But I mean, even if you have, then you need to work to make the data open, available, easily usable, and to make a challenge, to maintain the data sets. And this is something that needs a community behind it. That's
Well, thanks very much, Luca. This is fascinating. Thank you very much.
Just if I may add to that, just for the discussion, for the sake of discussion, that I fully agree on this, that we need these test cases and all these issues. But on the other hand, all these methods are more or less problem specific. And the protein folding is a very, very specific problem. I mean, you have a clear configuration of the minimum energy. And of course, as you say, you have huge and tons of data. So it's really not comparable with much more complex, let's say, when you have underlying PDFs that have multimodal and with much more different cases. But you're absolutely right that we need to make our, let's say, our problems appealing for these people or for the community in general.
Yeah.
It's too bad, Luca, that you are not here. Now we go for dinner and we discuss all this.
It's too bad for me.
Yeah,
With
exactly.
good wine,
We can invite him.
It's not fair, Luca, that you're not here with us.
Yeah, that's true.
Next time,
Next time.
Next time we'll invite him to come, of course, if he wants to.
With pleasure.
Oh, he should go. Oh, he's coming for Activate. Luca.
Yeah, it's true. When do we know when we have the kickoff meeting already or not?
I should, but I don't remember. Sometime in the summer, Luca. Sometime in the summer, I believe.
Okay.
And we have the furloughs.
Okay.
Yeah.
So thank you very much for the invitation.
Well, thank you, Luca. Thank you.
Okay. Thank you very much. Thank you very much, Professor.
Keep in touch.
Thank you very much.
Bye.
Yeah. We'll see you in the summer then.
Bye.
Bye-bye.
Thank you.
Bye-bye.